School buses are involved in more than 30,000 accidents each year. Several thousand children are injured. The Institute of Transportation and Traffic Engineering of the University of California at Los Angeles was asked to survey the problem. These are the first scientifically conducted programs to determine crash performance standards for bus bodies and safety equipment. A Mack Superior coach and a 60-passenger GMC Superior coach are ready for the first test, a head-on collision. 37 anthropometric dummies are installed in the new bus. Each dummy is equipped with electronic transducers to measure and record the accelerations and forces of impact. They simulate the size, weight, and collision movements of humans. 10 different types of seats will be evaluated as to the safety of their design and anchorage. Various seat belts and attachments will be studied. Along with special restraint bars, armrests, and airbag restraints. The first experiment will represent the most violent of the three major types of bus accidents: the head-on collision. School buses are exposed to the same hazards of everyday traffic as automobiles. How safe is the interior design of today's buses? What parts of the bus interior represent the greatest hazards in a head-on collision? Some of the answers will be learned in experiment number 86. Both buses will travel at 30 miles an hour. All over in less than 2 seconds. The same test again. On the old bus, the bumper is higher. It overrides the newer bus. The passengers are thrown forward violently into the seat backs ahead. Or flung missile-like over the lower seats. The passenger compartment to chassis attachments of the new bus failed. The bus body has moved forward 17 inches. and buckled the floor pan behind the driver's seat. The collapsed doorway would make it very difficult to get to the injured. Escape routes are too few and of inadequate design. School buses need at least 4 full-size emergency escape doors of standard design and location. School buses pick up and discharge passengers in a stop-and-go traffic cycle. The many stops expose school buses to their most frequent type of accident, the rear-end collision. In the UCLA rear-end collision test, the new bus will be impacted by a sedan moving at 60 miles an hour. In this type of accident, whiplash is the most frequent injury. The seriousness of the injury is generally related to the height of the seat back. With a violent whiplashing of the unsupported heads, some would develop critical injuries. Every passenger in a low seat back suffers whiplash. Accelerations as high as 106 Gs are recorded on the passengers' heads. Again, the bumpers do not meet. They're not of standard height. The car underrides the bus all the way back to the instrument panel. The bumper heights for buses and trucks must be standardized to correspond with passenger cars. This will prevent underriding and minimize injuries to occupants of the smaller vehicles. The body fastening bolts shear under the impact. Obviously, the frame fastenings for these buses require improvement. The tremendous impact shoves the 17,500-pound bus half the length of a football field. Innumerable times each day, school buses carry their precious cargo through the crossroads of danger. This X of intersecting traffic too often marks the site of a side impact collision. In the final experiment, a new sedan will side impact the bus at 60 miles an hour. The actions of the various restraint systems are of particular significance. They should keep the passengers from striking side window glass or internal parts of the bus. A slow motion repeat. 1/20th of a second, and the front end of the car disintegrates. By 2/10ths of a second, an unexpected near rollover occurs. One of the passengers is thrust through the roof port. emergency escape side window flails open from the violent forces of impact. Bodies are tossed from side to side. Only 2 restraining devices are proving to be of practical value throughout these experiments. The others, for various reasons, are not feasible in school buses. Strong, well-padded armrests also provide vital lateral constraint. During a crash, flexible but strong glass will keep heads and arms from getting outside the vehicle, where they can be hurt more seriously. Glass should remain in place. From these 3 experiments, the research staff concludes that a thorough redesign of buses, especially the interiors, is absolutely necessary. Injury-producing rigid structures must be eliminated or relocated. Lap belts can be valuable, but they should not be installed for buses unless they have well-padded seats with backrests having adequate head support and of proper strength. The greatest single contribution to bus passenger safety in a collision is the well-padded, high-strength, high-back safety seat. Present-day school buses have a seat back height of between 18 and 20 inches. But these experiments have shown that any seat with a backrest less than 28 inches high virtually assures serious injury in a collision. What can be done? With the safety of children at stake, we cannot let the cheapest course of action determine bus construction and interior furnishings. Safety regulations must be uniform. Design criteria must be standardized for all states. Bumpers on all vehicles, buses, trucks, and passenger cars alike must be designed to effectively oppose one another. This will prevent deadly overriding and underriding. No passenger should be permitted to stand in the aisle. No one should be seated on improvised aisle seats. Finally, all seats must be designed for maximum safety. The problems have been identified. Major solutions have been offered. It's up to you to make the facts known, along with your wishes, to your elected officials, the manufacturers of buses, your local school boards, and other agencies in a position to make decisions on our children's safety. Whether or not you will continue to read such headlines depends on the action from you.